When we look back at the grand arc of human history, every major leap in civilization has been defined by the materials we learned to extract and shape. The Stone Age gave way to the Bronze Age when ancient societies discovered how to smelt copper and tin. The Iron Age forged the foundations of classical empires, and the industrial and digital revolutions were born when humanity mastered fossil fuels, steel, silicon, and rare earth elements. Every building we inhabit, every vehicle that transports us, and every piece of microelectronic circuitry in our pockets began as raw rock pulled from the crust of our planet. Yet Earth is a finite, closed sphere, and the modern global economy is consuming these non-renewable treasures at an unprecedented and accelerating rate. Today, humanity faces a profound industrial dilemma. The technologies required to power our clean energy transition and sustain our digital civilization, from high-capacity lithium-ion batteries and wind turbines to advanced semiconductors, hydrogen fuel cells, and quantum computing chips, depend heavily on a select group of dense, highly specialized metals. Elements such as lithium, cobalt, nickel, tellurium, and the ultra-rare platinum group metals, including platinum, palladium, rhodium, and iridium, have become the indispensable building blocks of the 21st century. Yet extracting these critical resources from terrestrial mines requires pulverizing entire mountains, generating billions of tons of toxic tailings, burning colossal quantities of fossil fuels, contaminating groundwater reserves, and navigating precarious geopolitical choke points. To understand why these vital elements are so extraordinarily scarce in Earth's crust, one must look back more than 4.5 billion years to the violent infancy of our solar system. During the formation of the planet, gravitational compression and the radioactive decay of short-lived isotopes caused the young Earth to melt completely into a churning sphere of magma. In a monumental planetary event known to geophysicists as the Iron Catastrophe or Planetary Differentiation, the densest materials sank under the influence of gravity towards the center of the planet. Heavy, siderophile or iron-loving elements such as gold, platinum, palladium, rhodium, iridium, osmium, and ruthenium, chemically bound with molten iron and drained into the deep planetary core and lower mantle, leaving the cooling outer crust almost entirely stripped of these dense treasures. The precious metals mined near Earth's surface today did not originate in the planet's primordial crust. Nearly 4 billion years ago, during an epoch known as the Late Heavy Bombardment, millions of rogue asteroids, comets, and protoplanetary fragments pummeled the solidified crust of the Earth. The gold in our wedding rings, the platinum in catalytic converters, and the rhodium in specialized industrial sensors are the shattered, pulverized remnants of ancient cosmic impactors that dusted the surface long after the core had permanently sealed away Earth's own native reserves. Every terrestrial mine on Earth is, in essence, sifting through the ancient debris of long-dead asteroids. Floating in the cold, silent void between the planets are trillions of pristine celestial wanderers that never coalesced into full-sized worlds. These asteroids are pristine cosmic time capsules, preserving the raw, unsegregated ingredients from which the planets were assembled. Because most asteroids never grew large enough to undergo planetary differentiation, their heavy metals never sank to an inaccessible core. Instead, their precious elements remain distributed throughout their bodies, accessible directly from the surface. A single metallic asteroid just 500 meters in diameter can contain more platinum group metals than humanity has extracted throughout the entire recorded span of civilization. For more than half a century, space exploration was the exclusive domain of superpower governments, driven by national defense, ideological competition, and scientific curiosity. But over the last 2 decades, a monumental paradigm shift has fundamentally transformed the aerospace sector. The advent of reusable rocketry, high-performance commercial computing, miniaturized robotic instrumentation, and billions of dollars in private venture capital has unlocked deep space. What was once considered the distant, speculative realm of science fiction has rapidly transformed into a fierce, high-stakes commercial race, the quest to mine the boundless mineral wealth of the solar system. To comprehend the astronomical commercial potential of this new frontier, one must examine the taxonomy of the asteroid population. Asteroids are broadly categorized into 3 primary spectral classifications based on their composition, reflectance, and evolutionary history. The most common variety, accounting for roughly 75% of all known asteroids, are the C-type or carbonaceous chondrites. These ancient charcoal dark bodies are rich in organic carbon compounds, nitrogen, phosphorus, and most crucially, volatile water trapped chemically within hydrated clay minerals and phyllosilicates. The second major category consists of S-type or siliceous asteroids, which make up about 17% of the known population. Composed predominantly of iron and magnesium silicates, these stony bodies also contain substantial concentrations of nickel, cobalt, and precious metals. The third and most commercially dazzling classification is the M-type or metallic asteroids. Accounting for approximately 8% of known asteroids, M-type bodies are believed to be the exposed metallic cores of ancient protoplanets that were violently shattered during the chaotic collisions of the infant solar system. Composed of nearly pure nickel-iron alloy, they are enriched with staggering concentrations of platinum, gold, rhodium, and iridium. Among the most famous of these metallic giants is 16 Psyche, a massive asteroid orbiting in the main asteroid belt between Mars and Jupiter. Spanning more than 220 kilometers in diameter, Psyche is essentially a planetary core drifting naked through space. If the pure metal content of 16 Psyche were calculated at current terrestrial market prices, its theoretical value would exceed $10 quintillion, an incomprehensible sum thousands of times greater than the combined annual gross domestic product of every nation on Earth. Yet, despite sensational headlines, the private companies racing to mine asteroids are not planning to drag massive metallic boulders back to Earth to make their founders trillionaires overnight. Economists and aerospace analysts understand that basic laws of supply and demand govern global commodities. If a private mining enterprise were to return hundreds of metric tons of pure platinum or rhodium to Earth, it would instantly flood global markets, driving commodity prices down to near zero and destroying the profitability of the return mission. The true commercial gold rush in space is centered around a resource far more fundamental, urgent, and economically transformative than platinum or gold. That resource is ordinary water. In the unforgiving mathematics of space travel, water represents life support, radiation shielding, and above all, the foundational propellant required to power an interplanetary space economy. To understand why water is the most valuable substance in space, one must examine the tyranny of the rocket equation, formulated by Konstantin Tsiolkovsky. Launching any mass out of Earth's formidable gravitational well requires burning massive quantities of chemical fuel. Because that fuel itself has mass, a rocket must carry additional fuel just to lift the fuel it needs later in the flight. As a result, Lifting a single kilogram of water, food, or propellant from the surface of the Earth into low Earth orbit historically cost tens of thousands of dollars. And even with modern reusable rockets, it still costs thousands of dollars per kilogram. If private companies can extract water from nearby carbonaceous asteroids, that water can be converted directly in space into chemical rocket fuel. Through solar-powered electrolysis, water molecules are split into liquid hydrogen and liquid oxygen, the most energetic chemical propellant combination utilized in rocketry. Alternatively, the water can be used directly in thermal steam thrusters, water plasma thrusters, or electrothermal propulsion systems to maneuver orbital tugs and cargo vessels across the solar system. This concept, known across the aerospace industry as in situ resource utilization, or ISRU, is the cornerstone of the emerging cislunar economy. Asteroid-derived water can be stored in orbital refueling depots positioned strategically in low Earth orbit, geostationary orbit, and at the gravitationally stable Lagrange points between the Earth and the Moon. Spacecraft leaving Earth will no longer need to carry the massive burden of their return fuel out of Earth's gravity well. Instead, they can launch with empty propellant tanks, rendezvous with an orbital propellant depot, fill their tanks with asteroid fuel, and journey to the Moon, Mars, or deep space at a tiny fraction of the cost. Water also serves as the ultimate life support asset for human spaceflight. Beyond providing drinking water and breathable oxygen, water is one of the most effective radiation shields known to science. The hydrogen atoms in water molecules are exceptionally proficient at absorbing and deflecting high-energy galactic cosmic rays and solar particle events. By lining the hulls of space stations, lunar bases, and interplanetary transit vehicles with bladders of asteroid-derived water, astronauts can be shielded from lethal cosmic radiation without launching heavy shielding materials from Earth. Scientific confirmation of these volatile riches has advanced from theoretical models to direct empirical reality. Robotic sample return missions conducted by national space agencies, such as Japan's Hayabusa 2 mission to asteroid Ryugu and NASA's OSIRIS-REx mission to asteroid Bennu, have physically delivered pristine primordial material to terrestrial laboratories. Rigorous chemical analysis of these returned samples confirmed that carbonaceous near-Earth asteroids contain substantial percentages of bound water, carbon-rich clays, nitrogenous compounds, and complex prebiotic organic molecules, proving conclusively that asteroids are veritable chemical gold mines waiting to be harvested. When evaluating target asteroids for commercial mining, location and orbital mechanics are just as vital as mineral composition. While the main asteroid belt between Mars and Jupiter contains billions of asteroids, reaching the main belt requires immense amounts of energy and years of flight time. Consequently, the immediate focus of the private asteroid mining industry is not the main belt, but rather near-Earth asteroids, commonly known as NEAs. Near-Earth asteroids are celestial bodies whose orbital paths bring them within 1.3 astronomical units of the Sun, periodically intersecting or sweeping close to Earth's orbit. Astrodynamicists measure the difficulty of reaching a destination in space using delta V, which represents the total change in velocity required to transfer from one orbit to another. Remarkably, thousands of near-Earth asteroids have orbital trajectories that require less delta V to reach and return from than the surface of our own Moon. For an asteroid traveling on a similar orbital plane and velocity as Earth, a spacecraft requires only a modest propulsive burn to rendezvous with the rock, making these near-Earth objects the most energetically accessible territory in the entire solar system. Specific near-Earth targets have already been identified by orbital astronomers as premier candidates for early commercial harvesting. Asteroid 1986 DA, for example, is a 2-kilometer-wide metallic near-Earth asteroid whose spectral signature indicates a composition of 90% high-grade iron-nickel alloy alongside billions of dollars worth of platinum group metals. Similarly, near-Earth carbonaceous bodies like 3554 Ammon, 4660 Nereus, and 16273 Ryugu offer low delta-V trajectories that make automated robotic extraction missions both physically feasible and commercially viable with existing aerospace propulsion technologies. The race to capture these resources is not the first time private enterprise has set its sights on the asteroid belt. In the early 2010s, the first wave of commercial asteroid mining emerged with great fanfare. Pioneering startups such as Planetary Resources and Deep Space Industries raised tens of millions of dollars from prominent tech billionaires, attracting top aerospace engineering talent and capturing the imagination of the global public. They unveiled ambitious roadmaps to launch fleets of orbital prospecting telescopes and robotic mining vessels to capture near-Earth asteroids. However, this first wave arrived nearly a decade too early. In the 2010s, the commercial launch market was still dominated by expensive, expendable rockets, making regular deep space missions financially prohibitive. Autonomous navigation and deep space robotics were still in their infancy.
Most critically, there was no existing in-space infrastructure or commercial customer base to buy extracted water and propellant. When venture capital funding tightened, these early pioneers were forced to pivot their technologies toward Earth observation and small satellite propulsion before ultimately being acquired, leaving behind a valuable roadmap of lessons for the next generation. Today, the landscape has fundamentally transformed. The primary catalyst driving the second wave of asteroid mining is the dramatic collapse in launch costs. The development and perfection of reusable rockets, led by commercial space companies, dropped the cost of reaching low Earth orbit by more than 90%. Launch costs that once exceeded $20,000 per kilogram have fallen below $2,000. And the advent of next-generation, fully reusable, super-heavy launch systems promises to push costs below a few $100s per kilogram. This dramatic reduction in launch costs has shattered the financial barrier that doomed the first generation of space resource companies. Simultaneously, a thriving cislunar ecosystem is emerging. Commercial space station developers, lunar lander companies, satellite servicing fleets, and national space agencies participating in lunar exploration programs have created a rapidly growing customer base with an urgent demand for off-world propellant, water, and structural materials. For the first time in history, the market demand for in-space resources is real, funded, and expanding rapidly. The dynamic second wave of private asteroid mining companies has stepped forward to seize this opportunity. Companies like Astroforge, Transastra, Karman Plus, Orbit Fab, and Interloon are pursuing practical, highly focused business strategies. Rather than attempting to build massive all-in-one mining complexes from the outset, these companies are executing modular, phased approaches, first deploying low-cost robotic prospectors, then establishing orbital fuel depots, and finally extracting specific high-value metals and volatiles using purpose-built technologies. The mining lifecycle begins with high-precision robotic prospecting. From ground-based optical and radio telescopes, an asteroid appears only as a faint, shimmering point of light. To determine whether a target asteroid is a solid metallic treasure trove, a volatile, rich carbonaceous body, or merely a loose, structurally fragile rubble pile held together by whisper-thin gravitational forces, private mining companies must deploy specialized robotic scouts. These prospecting spacecraft, often built on agile CubeSat and SmallSat platforms, are equipped with sophisticated remote sensing suites. Multispectral and hyperspectral cameras analyze the reflected solar radiation across visible and infrared wavelengths to map surface mineralogy. Gamma ray and neutron spectrometers measure cosmic ray interactions with the asteroid's surface to quantify the abundance of iron, nickel, hydrogen, and volatile elements. High-resolution, laser altimeters, and radar systems map the topography, rotational dynamics, and internal mass distribution, providing the precise navigation data needed for an extraction spacecraft to approach safely. Once a target asteroid is characterized, the extraction craft must solve one of the most formidable engineering hurdles in aerospace: operating in microgravity. On Earth, gravity anchors massive bulldozers, drills, and excavators firmly to the ground, allowing heavy machinery to exert thousands of pounds of downward mechanical force. On an asteroid measuring only a few hundred meters across, the gravitational pull is practically negligible, millions of times weaker than on Earth. An astronaut, standing on the surface, could jump into space with the power of their leg muscles, and a mechanical drill pressing into the rock would simply push the spacecraft backward into the void. To overcome this physical barrier, private engineers have developed revolutionary anchoring and containment architectures. Some systems utilize microspine grippers, hundreds of tiny, curved mechanical claws inspired by gecko and insect biology that latch onto micro-roughness in the rock surface to lock the spacecraft in place. Other concepts deploy helical drills and harpoons that penetrate deep into the regolith to secure tension cables. One of the most elegant extraction paradigms is optical mining, pioneered by companies like Transastra. In this approach, a spacecraft approaches a small carbonaceous asteroid and deploys a giant, ultra-lightweight inflatable containment enclosure that completely envelops the celestial body. Once the asteroid is sealed inside the translucent membrane, large deployable parabolic solar concentrators focus intense, unfiltered sunlight directly onto the asteroid's surface. The concentrated solar thermal energy generates localized temperatures exceeding 1,000 degrees Celsius. This intense heat causes the hydrated minerals and volatile compounds within the rock to fracture and vaporize in an explosive physical process known as thermal spallation. The water vapor, carbon monoxide, carbon dioxide, and organic gases outgas rapidly from the rock, filling the containment enclosure. Because the entire asteroid is enclosed within the bag, no volatile gases or valuable dust particles can escape into the vacuum of space. The vaporized gases are drawn through specialized filtration ducts into cryogenic cold traps. In the deep freeze of the containment shadow, the water vapor rapidly condenses and sublimates directly into solid ice, separating cleanly from the dust and rocky debris. The ice can then be melted, purified, and transferred into orbital propellant tankers without requiring complex mechanical crushers or hazardous chemical reagents. To transport these extracted volatiles and harvested ores efficiently back to cislunar depots, engineers rely on advanced high-efficiency electric propulsion systems. Solar electric propulsion, utilizing Hall-effect thrusters and gridded ion engines powered by massive solar arrays, provides specific impulses 10 times higher than traditional chemical rockets. Operating continuously over months using propellants such as xenon, krypton, or asteroid-derived iodine and water plasma. These ion tugs can haul hundreds of tons of purified resources across interplanetary space with minimal fuel mass. For metallic M-type asteroids, private companies are pursuing entirely different harvesting methodologies designed to capture pure native metals. Over billions of years, micrometeoroids have continuously pulverized the surfaces of metallic asteroids, generating a thick outer blanket of loose, granular metallic regolith, rich in iron, nickel, and platinum group elements.
Because these grains are highly magnetic and electrically conductive, robotic harvesters can sweep low-energy magnetic drums and electrostatic collection rollers across the surface, gathering tons of concentrated metallic ore without needing to drill into solid bedrock. To refine and purify this metallic regolith in the vacuum of space, aerospace chemical engineers are adapting proven industrial gasification techniques, most notably the Mond-Carbonyl process. In this chemical cycle, crushed metallic regolith is heated inside a closed reaction vessel and exposed to carbon monoxide gas at moderate temperatures of approximately 50 to 100 degrees Celsius. Under these conditions, nickel and iron react readily with the carbon monoxide to form volatile gaseous metal carbonyls, specifically nickel tetracarbonyl, and iron pentacarbonyl. Because the platinum group metals, gold and silicate impurities, do not react with carbon monoxide at these temperatures, they remain behind in the reaction chamber as a highly concentrated, enriched solid residue, which can be collected and returned to Earth or used for advanced manufacturing. Meanwhile, the gaseous iron and nickel carbonyls are separated through fractional distillation and then heated to roughly 230 degrees Celsius. At this temperature, the carbonyl gases decompose, releasing the carbon monoxide gas to be recycled back into the system and leaving behind ultra-pure spherical powders of metallic iron and nickel. An alternative metallurgical method gaining momentum is molten regolith electrolysis. By heating raw, unrefined asteroid silicates and metal ores to temperatures above 1600 degrees Celsius in an electrolytic cell, electric currents separate the molten slag directly into liquid metals such as pure iron, silicon, titanium, and aluminum, while releasing pure oxygen gas as a byproduct. This dual output process provides both the structural metals needed for orbital manufacturing and the life-giving oxygen required for breathing and rocket propulsion, creating a completely closed-loop industrial cycle in the vacuum of space. These ultra-pure metal powders and molten alloys can be fed directly into advanced electron beam and laser additive manufacturing systems operating in orbit. This capability unlocks a transformative technological paradigm: in-space manufacturing. On Earth, every satellite, space station module, and space telescope is fundamentally limited by the narrow diameter and strict mass constraints of rocket payload fairings. Furthermore, terrestrial space hardware must be engineered with massive structural reinforcement simply to survive the violent acoustic vibrations and crushing G-forces of atmospheric launch. When structural materials are mined from asteroids and manufactured directly in microgravity, those launch constraints disappear entirely. Engineers in orbit can 3D print lightweight, gossamer structures on a scale that would collapse under their own weight on Earth. We can construct astronomical observatories with segmented primary mirrors hundreds of meters across, capable of directly imaging the atmospheres and weather systems of distant terrestrial exoplanets. We can assemble gigawatt-scale space-based solar power satellites that collect unfiltered sunlight in geostationary orbit and beam clean continuous electrical power down to Earth via safe microwaves, eliminating the intermittency of terrestrial renewable energy. Beyond mechanical and chemical processing, synthetic biologists and private biotechnology ventures are pioneering the field of biological mining, or bioleaching. On Earth, specialized extremophile bacteria and archaea, such as Acidithiobacillus ferrooxidans, naturally break down sulfide and iron ores, dissolving and concentrating valuable metals from low-grade rock. Synthetic biologists are engineering robust, radiation-resistant microbial strains designed to thrive inside sealed bioreactors in microgravity. These engineered microbes can digest pulverized asteroid regolith, selectively extracting rare earths, copper, cobalt, and precious metals with minimal energy consumption and zero toxic chemical waste. As private companies demonstrate the technical feasibility of asteroid mining, the race has triggered profound legal, geopolitical, and regulatory transformations. For decades, international space law was anchored by the 1967 Outer Space Treaty, drafted during the Cold War when only nation-states possessed the capability to launch satellites. Article 2 of the treaty explicitly states that outer space, including the Moon and other celestial bodies, is not subject to national appropriation by claim of sovereignty, by means of use or occupation, or by any other means. For years, legal scholars vigorously debated whether this prohibition applied only to sovereign nations claiming territory, or if it also prohibited private commercial enterprises from extracting and selling resources. If a private company spends hundreds of millions of dollars to harvest water or metal from an asteroid, does it legally own that material? Or is it the common heritage of all humankind? To resolve this regulatory ambiguity and provide legal certainty to investors, the United States passed the Commercial Space Launch Competitiveness Act of 2015, widely known as the Space Act. This landmark legislation explicitly granted American citizens and private corporations the legal right to own, possess, transport, use, and sell any abiotic space resource, including water and minerals, extracted from asteroids or the Moon in accordance with applicable international obligations. Other forward-thinking nations quickly followed suit. In 2017, the Grand Duchy of Luxembourg enacted a comprehensive national legal framework providing guaranteed property rights for space resources and established an investment fund to support commercial space startups, positioning the country as the premier European hub for asteroid mining ventures. Similar legislation has since been enacted by the United Arab Emirates and Japan, creating a robust international legal foundation for commercial space extraction. Space legal experts frequently draw a direct analogy between asteroid mining and international maritime law. Under the United Nations Convention on the Law of the Sea, no sovereign nation can claim ownership over the international high seas or the seabed beneath them. However, when a private commercial fishing vessel pulls fish from international waters or an energy company extracts oil from deep offshore reserves, the harvested resources belong indisputably to the commercial entity that performed the extraction. In the exact same manner, private asteroid miners do not claim sovereignty or ownership over the celestial body itself. They own the specific water ice, volatile gases, and refined metal ingots they harvest and process. To establish broader international consensus around these commercial norms, the United States, in partnership with more than 40 nations, introduced the Artemis Accords. Grounded in the principles of the 1967 Outer Space Treaty, the Accords establish common rules of conduct for civil and commercial space exploration, explicitly affirming that the extraction and utilization of space resources is fully compliant with international law. The Accords also establish the concept of transparent safety zones around mining and exploration sites to avoid harmful interference between competing operators. Simultaneously, other major spacefaring nations, including China and Russia, are advancing their own international lunar and deep space resource architectures, such as the International Lunar Research Station. As commercial interest in asteroid resources accelerates, the development of off-world mineral wealth is rapidly becoming one of the most critical geopolitical competitions of the 21st century, determining which nations and private coalitions will establish the foundational supply chains of the solar system. Beyond economic wealth and geopolitical influence, the private race to mine asteroids carries a monumental secondary benefit that could one day safeguard the very survival of human civilization: planetary defense. Throughout the 4.5 billion-year history of Earth, catastrophic asteroid impacts have repeatedly reshaped the planet's biosphere, causing mass extinctions like the Chicxulub impact 66 million years ago that ended the reign of the non-avian dinosaurs. The engineering capabilities required to prospect, track, rendezvous with, grapple, and alter the trajectory of near-Earth asteroids for commercial mining are identical to the technologies required to deflect a hazardous asteroid on a collision course with Earth. Technologies such as kinetic impactors, gravity tractors, laser ablation thrusters, and optical mining mass expulsion all provide practical means to redirect an incoming celestial body. By developing a self-sustaining commercial asteroid mining industry with fleets of robotic spacecraft operating across the inner solar system, private enterprise is inadvertently constructing a permanent, automated planetary defense shield for our homeworld. Perhaps the most profound promise of asteroid mining lies in its potential to heal the terrestrial environment. Terrestrial mining is one of the most destructive industrial activities on the planet, responsible for widespread deforestation, contamination of pristine water tables, toxic acid mine drainage, and significant global greenhouse gas emissions. As the world transitions away from fossil fuels toward electrification, global demand for battery metals and critical minerals will expand exponentially. If we continue to extract these vast quantities exclusively from Earth's delicate biosphere, we risk causing catastrophic ecological damage in our pursuit of clean energy. Moving heavy mining and refining operations off-world provides the ultimate ecological release valve. Asteroids possess no ecosystems to destroy, no atmospheres to pollute, and no indigenous life to displace. In the vast vacuum of space, industrial refining can be powered entirely by continuous, abundant solar energy, with zero environmental impact on Earth. As the visionary physicist Gerard K. O'Neill articulated decades ago, Earth could eventually be preserved as a residential and agricultural paradise, while the dirty, energy-intensive, extractive industries that sustain technological civilization are relocated into the sterile, resource-rich expanse of space. On the grandest cosmic scale, mastering the mineral and energy wealth of the asteroid population represents humanity's monumental transition toward becoming a Kardashev Type 1 civilization, a species capable of utilizing the full energetic and material potential of its planetary system. The private companies racing to mine asteroids are not merely pursuing corporate profit or chasing speculative dreams. They are building the indispensable industrial infrastructure for an interplanetary civilization, transforming humanity from a fragile single-planet species into a permanent, multi-planetary presence across the stars.